That's going to go with that. All right, we'll say welcome everyone on YouTube. We are resuming the recording here in the room. I believe we are recording and streaming to YouTube now. Welcome everyone to the next Water, Wetlands, and Watersheds seminar. Megan, give me a big thumbs down if everything is like going awfully. All right. So thank you very much. We have our speaker today zooming in from Orlando. So our seminar today is by Dr. Kelly Kibler. Excellent. And Dr. Kibler is an associate professor of water resources engineering in the Department of Civil, Environmental, and Construction Engineering at the University of Central Florida. She's a faculty of UCS National Center for Integrated Coastal Research and a faculty fellow of UCS Center for Global Economic and Environmental Opportunity. Dr. Kibler has her PhD in water resources from Oregon State University. Go Ducks?
No, Beavs.
Beavers. All right, sorry. Go Knights, I guess. Before joining UCF, she worked at the UN Environmental, Scientific, and Cultural Organization, so UNESCO, which you all have heard of. Her lab focuses on interdisciplinary research about water resources engineering and aquatic ecology. And she's done a lot of really interesting biophysical interaction work, so flow biology interactions, and obviously we'll see something about oysters today and maybe a couple of others as well. Dr. Kibler's research findings are applied to the design of natural infrastructure, so very relevant to a lot of what we're studying here at the Center for Coastal Solutions and ESSE, and attempting to protect communities from climate hazards like erosion and flooding. So Kelly, the floor is yours, and I'll let you know, it looks like everything's going well, so thank you two for your patience, and yeah, go ahead, Kelly.
Well, good afternoon, everyone. It's really an honor to be invited here to talk to you today about my research. I wish I could be there in person, but I had to give a fluid mechanics lecture in my course this morning in Orlando. So coming to you virtually is the best I can do today. But really excited to be here and talk about my research group's study of hydrodynamics and sediment transport in complex biological canopies, like you can see in this picture here of an intertidal oyster reef. And especially about how that science can translate into robust design of natural living infrastructure. So here's just a roadmap of where we're going to go today. So I'm going to just start with a quick introduction about ecohydraulics research and really focus on the applications to natural infrastructure design. And then we'll talk about the influence of biological canopies, how they affect hydrodynamics and sediment transport. And then we'll kind of flip that around and look at how hydrodynamics and the prevailing sediment environment are going to affect the development of biological canopies. So this is kind of how I define ecohydraulics as an interdisciplinary study of coupled physical and biological variables in aquatic systems that can be natural systems or engineered. So I like to use this little graphic where we've got kind of the traditional engineering disciplines, hydrology, hydraulics, and then those are married to geosciences, river mechanics, and sediment transport. And then we throw in a little bit of the aquatic ecology and biology, stream and estuarine ecology. So basically, when a moving fluid is water and it touches something that's alive, I can find some ecohydraulics happening there.
That's great. I love that definition, Kelly. That's awesome.
Thanks. So there's a lot of applications to what is called natural infrastructure. So if we conceptualize ecosystems as being a part of our essential infrastructure, it makes a lot of sense, right? They provide a lot of essential services that humans value, like clean water or buffering of climatic extremes or maintaining some stable, safe places for humans to live our lives. And through the years, I've seen a number of different names for this idea of ecosystem as infrastructure. I kind of group them like you can see here, where, green infrastructure is usually referring to urban or suburban stormwater management of some sort. And then we've got natural and infrastructure and nature-based solutions. We're a bit more general and somewhat related to one another. So the natural infrastructure refers to natural systems, intact or restored systems like wetlands or forests, reefs, whereas the nature-based approaches mimic these natural systems, but they're designed and constructed by humans. So both have the same effect of being able to benefit society. Some of the things that my group is concerned about are things like risks of weather and climate-related hazards, which natural infrastructure can certainly help out with, while providing other really essential ecosystem services, usually called co-benefits, So things like providing that biogeochemical cycling that gives us the clean water, or provisioning habitat for biodiversity, sequestering carbon, all kinds of really important things. So if we frame ecosystems as infrastructure, that allows us to make some really good comparisons in terms of cost and performance as compared to the traditional engineered solutions that would have been used. And there are some really clear advantages to the natural infrastructure. The first is that nature-based designs are really harnessing that power of evolutionary experience, because healthy, intact ecosystems have been adapted to the natural disturbance patterns. They have the capacity to withstand or recover or even become stronger from that climatic variability. And even a really, really good engineered traditional like concrete design doesn't have that type of learning that's been integrated over decades, centuries, millennia, that evolutionary kind of time scale. Number two, the natural infrastructure has the ability to adjust as the environmental conditions around it change. Again, if I'm going to build something out of concrete, I have to choose one design elevation, and it's going to stay static even as things change around it, like the ground surface level maybe, or the water level, whereas something that's alive can adapt to the exogenous conditions. And then if the natural infrastructure is designed and conceptualized appropriately, essentially could maintain itself for theoretically unlimited design lifespan. So from an engineer's perspective, when we see these number 3 and 4, that's like a win-win. We're always looking to reduce costs of operation and maintenance and improve design lifespans. And that's why there's been really kind of a veritable explosion of interest in natural infrastructure over the recent decades. So here's just a few recent US policy decisions that have been made, really highlighting investments in natural infrastructure. And a lot of this is coming from a place of just realization from communities that even if we make historic investments into protecting infrastructure from climate change and sea level rise, we're still not going to be able to save every place all the time using traditional methods. We really need to be looking out of the box at new technologies. And so one application of ecohydraulics research is to the design of natural infrastructure. And my lab really focuses on the study of biological canopies. So biological canopies can be seen as kind of a porous obstruction to flow, and one that is able to adapt to the hydrodynamic and sediment transport regime. And the canopy interacts with the flow in 3 spatial dimensions, and that varies over time as the conditions like water level or flow speed or direction change. And these canopy properties are really a primary control to the flow canopy interaction that develops. These also change over time in response to the prevailing hydrodynamic and sediment transport environment. So you have this great dynamic feedback that exists between the biological canopy and the external environment. So the most kind of classic of these feedbacks is the positive feedback that a living canopy creates for itself. It creates the conditions that are going to allow it to grow, reproduce successfully. And that's why these organisms are often referred to as ecosystem engineers, because they engineer the conditions that are advantageous to them. So I've got kind of 2 ecohydraulics research questions that sum up everything that my lab really does, and then their application to how we would apply them to design. So number 1 is, how do these complex biological canopies alter the flow field, hydrodynamics, and how does that translate into changes in sediment transport and retention? So kind of like this example video I've got for you here, we've got a natural intertidal oyster reef. And you can see that there's some little, micro waves coming in and hitting the reef. And then the reef really changes the way that the flow field is moving so that the water behind the reef is nice and calm and still.
Welcome everyone on YouTube. We're resuming the recording here in the room. I believe we are recording and streaming to YouTube now. Welcome everyone to the next Water Wetlands. Mute that person just a moment. They can give me a big thumbs down if everything is good. Okay. Go ahead, Kelly.
Okay, great, thanks. So if we were going to try to create some sort of nature-based design that does something similar to what this reef is doing, we would want to be thinking about how that living design is going to change the local environment. Is the design going to be efficacious to promote sediment deposition kind of between that reef and the shoreline area? So the second ecohydraulics research question is, how does that hydrodynamic environment shape the living environment? And this really has to do with creating a design that is robust to the external environmental conditions. So a couple of just quick ideas about the methods that my lab usually employs. We do lab experimentation in flumes, we do numerical modeling, but I think the most important thing that we engage in regularly is observation of hydrodynamics and sediment transport in complex biological canopies, right? These are difficult things to create in a lab or even numerically. We don't even really know sometimes the correct way to parameterize the processes that are happening in these complex flow fields. So it becomes really important for us to observe things that are happening in actual aquatic ecosystems. So let's say that we want to ask how a particular biological canopy affects the flow field. We may set up a cluster of instruments in an unobstructed flow out here in the channel, and then a similar kind of instrument cluster within whatever canopy it is that we're studying and compare the difference. We use a lot of acoustic-based instruments to measure things like flow speed. We use pressure-based sensors for things like water depth or wave parameterizations. Optical instruments to measure how much mass is being moved within the water column. And a lot of times we'll position our instruments in various places within the canopy. So in the little cartoon I've got for you over here, both embedded right down inside of those little clusters of oysters and then maybe above it to see how things are changing throughout the boundary condition. So properties of the biological canopies that control flow canopy interaction, we can kind of think about in a framework of being whether or not that canopy is emergent all the way through the water column versus submerged, if the organism is rigid or if it bends and flexes under the influence of flow, and then how many elements are there per unit area or how much volume is being displaced from within the water. So this gets into the idea of canopy density. So these are some pretty important properties of the canopies that we need to record, as well as whatever the environmental variables that we are measuring. So my lab spends a lot of time measuring things and counting things. Here's some more measuring and counting. And sometimes we get really, really frustrated by how much measuring and counting has to be done. And so we've developed a few kind of new methodologies, for instance, using laser scanning to scan an entire oyster reef canopy that we can then take that three-dimensional point cloud and parameterize it into roughness at a fairly fine spatial scale. So we could know things like the height of the canopy, or its rugosity or fractal dimension, but over the scale of an entire reef, which is not possible if you're just quadrating and counting oysters. So speaking of measuring and counting things, we also do a lot of measuring and counting of sediments, whether it's mass suspended in the water column or counting the amount of mineral versus organic sediments that are in a location through bulk sampling, or doing repeat surveying to understand in a particular area over time has more sediment eroded or been deposited. So that's just a brief overview of some of the methods. And now I'll get into showing you some data. So first, we're going to tackle that first research question. So how are these biological canopies altering hydrodynamics? The first canopy I'm going to talk about is vegetation. So we're looking at emergent all the way through the water column and rigid, so not deforming under flow. And what we see, so in this middle plot, we've got the speed of flow in the channel. On the y-axis, we've got the speed of flow within the canopy, and we're comparing two different canopy types, one of mature mangrove forest and the other restored vegetation about 7 years old. And we see that they're really suppressing the flows, even as the flows in the channel increase and get as much as about 15, 20 centimeters per second. We're seeing everything within the vegetation very, very suppressed below 2 centimeters per second. Whereas in a nearby site with no vegetation, just kind of next to a seawall, there's a strong linear relationship between as the flow in the channel with speed increases, the flow near the shoreline also increases. And corresponding with that, we also see, if we look at turbulence on the left-hand side, that our two vegetated sites really have a lot higher levels of turbulence happening within the flow as compared to that seawall site. And if we look at wave attenuation, both of the types of vegetation are doing a good job at suppressing wave energy at about 30% or so, whereas that bare sediment seawall site is more like 5 to 10%. The second oyster canopy, this one is going to be a submerged canopy that is also rigid. And here I'm showing you some data that were collected by one of my former postdocs, Dr. Kit Sakoutis, who's at University of Twente in the Netherlands now. When you give these kind of talks, sometimes it gives the impression like I did all of this, but really there's a lot of people who contributed to collecting these data and doing the science that I'm showing you. So I'll try to introduce you to those folks as we go along. So in our second canopy type, this is a cool kind of comparison because we're looking here at the left at flows going through a mature, well-developed reference state oyster canopy. And then on the right-hand side, the reef is still there. The canopy has degraded. There's no longer a canopy on top of the reef. So you're still getting the hydrodynamic effect of the bed form of the reef. We're just able to look at the difference that the canopy makes. And gosh, it makes a big difference close to the bed. So in our flow over the degraded reef, we have this very strong hydrodynamic gradient that's happening close to the bed that is much more muted within the canopy. But what we're also seeing is a lot of creation of turbulence within the canopy as the flow interacts with these individual elements. A good example of an ecosystem engineer creating really good conditions for larval recruitment into the canopy. So oyster larvae are kind of cued to dive down when they see this particular signature of turbulence that's created within the canopy, and then they can find some nice hydrodynamic and predator refuges within that complex canopy. So after looking at these data, we kind of wondered, well, what if we do a similar look at what happens within the canopy of restored oyster reef? So if that degraded reef had been restored, and some time had gone by and some of the canopy had had time to develop, would it have a similar type of effect to hydrodynamics to what we have seen in that reference state canopy? And so what we find is that even very quickly after restoration, that hydrodynamic kind of relationship is restored very, very quickly. So here we're looking at data taken above the canopy on the left and nestled down within those oyster clusters on the right. We see high levels of energy attenuation, a little bit higher within the oyster clusters, of course, but this is happening almost immediately after restoration. Here we're looking at data across a couple of different restored reefs that have been restored anywhere from 1 to 4 years before we collected these data, and then as compared to that reference reef in green. The degraded reef, we also included a degraded reef in these data. There was no strong kind of correlation about channel versus reef velocities. There's no relationship there. So that's kind of exactly what we would see before restoration. As soon as the reef has been restored, we see this nice linear relationship develop. And if we take a kind of deeper look into what's happening in these kind of instantaneous hydrodynamic measurements, we can see some real differences happening to the turbulence signature of this restored reef over a period of 1 year. So pretty big lift in dissipation and production of turbulence over that first year of restoration. So what's happening is that as the reef is recruiting new oysters to it, and the density goes from 0 live oysters to over 300 live oysters per square meter, we're seeing kind of that intense turbulence queue start to develop. And so that got us thinking about, well, what is the influence of the density to the flow signature? So if we have a lot of oysters per square meter, does that produce a different flow signature than if there are fewer? So this is a study that one of my PhD students, Manisha Thanuara, took on. And so he studied 4 different sites of differing canopy densities, ranging from a sparse to a moderately dense to a dense clustered arrangement, and then a dense homogeneous relationship where we have increasing canopy density as we go through. These were all found in the same reef. And so what he found basically is that the canopy density really is giving us hydrodynamic destiny, very, very strong signature of hydrodynamics based on the canopy's density. When we look within the canopy, so kind of on the left-hand side, the top plot, for the most part, all densities of oyster reef are really attenuating a lot of hydrodynamic energy within the canopy. But then if we look at the position just over the top of the canopy, what we see here is a lot of differentiation based on density. And I want to draw your attention to this little cluster of dark green points that is above the 1-to-1 line. So what that's indicating is that the flow incident to the reef, so kind of coming into the reef on the x-axis, if we're measuring right above the oyster canopy, we're not seeing attenuation, but instead augmentation of the flow by the reef canopy. So what's happening is that the density of the canopy is just so great in this site that as the flow comes in, it's routed up and over, kind of like a jet over the top of the canopy, creating this nice turbulent and high velocity shear layer above the top of the canopy, while everything inside is staying nice and suppressed. If we look then at the turbulence, we do see a lot of difference depending on whether we're looking at a sparse versus a dense canopy. So our sparse and moderate canopies really have a very, very different scale of turbulence that's being created as opposed to our two denser canopy types. So there's one more property of biological canopies that I haven't talked about yet, and it might be, the one to rule them all. So here we're looking at a third type of canopy, seagrasses. So these are going to be submerged and flexible. So they're going to deform under the influence of flow. In this particular site, you can see kind of the canopy cover of seagrass that is mapped in the site map. So the dark red areas are places with a lot of canopy cover, more dense seagrass, and then the areas that tend towards the blue are sparser. So here we're asking what is the effect of the canopy's density to flow attenuation, and we're comparing to a site that has no seagrasses, bare. And so the bare site from the channel to the shoreline is already attenuating about 50% of the hydrodynamic energy just as the flow kind of approaches the channel margin. And as we move into a site that's characterized by about 2,500 blades of seagrass per meter squared, we see that that attenuation rate goes up, which is what is expected. But then if we go into our dense site, we actually saw less energy attenuated by the 8,300 blades of seagrass per meter squared than we even saw at the bare sediment site. So what's going on here? Well, our dense site that we chose happened to be just downstream of a much denser patch of seagrass. And so all of the flow, just kind of like it was coming into that very, very dense, homogeneous oyster canopy, instead of being able to penetrate through the canopy, it's finding any path of least resistance, which in this case is around the patch and right through the place where we're taking our data. So our area was densely vegetated, but it wasn't quite as densely vegetated as the areas around it. And so it became a preferential flow path. So what we learned from this, very humbling, is that the patch scale interactions and heterogeneity in the horizontal can really override some of these other really important canopy properties. So maybe the horizontal biological canopy configuration is really what is destiny for hydrodynamics. So far we have been talking all about hydrodynamics, but we're also really interested in the sediment transport ultimately. Why? Because there are so many applications of this question to bank stability or the mitigation of erosion or slowing down the conversion of wetland areas into open water, a ton of applications for this right now. So if we think about trying to stabilize an eroding shoreline using living infrastructure or nature-based solutions, let's consider the design of a submerged reef-like breakwater that might be implemented to protect that eroding shoreline. So of the total incident incoming hydrodynamic energy, up here in these orange colors, some of it's going to be reflected back off of the reef, some of it will be dissipated by waves breaking or drag on the top of the reef, and anything that's remaining is going to be transmitted and available to mobilize sediments, transport capacity on the backside of the reef. So if I put that into an energy balance, we really don't have an easy time breaking out some of these dissipated terms. So in practice, what we tend to do is just measure incoming hydrodynamic energy, measure it after the reef, and calculate a transmission rate. And there's a real temptation to conflate the hydrodynamic effect of this reef with performance in stabilizing the shoreline. So we might assume this nice linear relationship that greater amounts of energy attenuation would convey to greater amounts of sediment retention, but sediment transport is notoriously nonlinear, and we may be mistaken about that. So in thinking about shoreline stability, what we really want to be focusing on is the sediment budget. And if we have a situation of like an eroding shoreline, what that really means is that we have a greater transport rate of sediment leaving the shoreline than we have replacing it coming in. And when we develop some sort of living infrastructure, biological canopies in the vicinity of the shoreline, what we're attempting to do is kind of flip that transport rate so that more sediment is being retained and deposited into the shoreline instead of leaving, and over time increasing the bed elevation. Hopefully also leading to expansion of our vegetation community, recruitment of organisms onto this reef, so that over time, even as the sediment bed level comes up around our reef can grow and kind of keep pace with the sediment deposition rate. So that's ideally what we're trying to accomplish, and hydrodynamics certainly are the architect of the sediment budget dynamics, but the sediment transport dynamics are really what is providing for that shoreline stability. So that's kind of what we have to be paying a little bit more attention to. So if we get into kind of the classic sediment transport models for open channel flow, most, like the ones I've got shown here, the Meyer-Peter-Mueller equation or the Einstein-Brown equations, most are based on concepts of excess shear stress. So you can see shear stress is playing a pretty big role in both of these. And they both tend to have pretty poor fidelity within complex flow fields like biological canopies. And so we can look at why this is. So there are a couple of different ways that we can estimate the incident shear stress within complex flow fields, right? We can do momentum analyses. We can analyze shear stress based on logarithmic models of the flow profile, law of the wall. We can apply quadratic drag laws. All of these have some problems. So for momentum, this is going to give us a reach level mean of shear stress. That's not going to be sufficient within, a highly variable biological canopy. Our logarithmic model will not apply because flows within biological canopies are just not logarithmic. Quadratic drag law always is going to be problematic for us, trying to figure out what that darn drag coefficient is that changes with Reynolds number and position and, geometry of our canopy. So we can look into estimating our incident shear stress using turbulent methodologies. So for instance, calculating things like a Reynolds stress or estimating a turbulent kinetic energy K, or looking at variance just in the vertical if we're working in a wave-affected field. And so here are those same oyster reef data that we looked at earlier with shear stress being estimated underneath. In the degraded reef, all of the different methodologies that we use to estimate shear stress, they kind of collapse and converge at one particular answer. So whether we're looking at turbulence or whether we're looking at applying like a logarithmic model, we get about the same estimation of shear stress. But when we look in the oyster canopy, there's a lot more of a spread depending on the methodology that you use. And even within the turbulence methodologies, there's no really good agreement about what that shear stress is. And so what that tends to produce is that poor fidelity of traditional sediment models in vegetation or complex flow fields like biological canopies. And these data actually really conceptualize the problem very well. So these were done experimentally in a flume by Yang and Knepp in 2018. And so what we're looking at here is the Einstein-Brown sediment transport rate. So that's the model that's shown with the black line. And then the black dots are all flume data collected. And the colored circles and triangles are the data that the authors collected. So the dark blue triangles are with no vegetation or simulated vegetation in their flume, just a bare sediment bed. Everything lines up pretty well with the Einstein-Brown model. As we start increasing the density of canopy elements over here with the colors, the data start diverging more and more from the prediction. So again, we're seeing that very, very poor fidelity of traditional sediment modeling in complex flow fields. So what Yang and Knepp have done is they've translated that Einstein-Brown sediment model using turbulence-based methods, and all of a sudden, all of the vegetation is being predicted pretty well by this sediment transport model. So they're able to improve the model fidelity by replacing shear stress with turbulence. Why is this? Well, because the element-generated turbulence is enhancing sediment transport rate. What that means is for a given flow, the sediment transport rate is going to be higher when there is canopy than when there is not canopy. So the problem comes where we think about what we actually see in aquatic ecosystems, and usually it looks something like this. When you've got vegetation, there's usually a big retention of sediment that's happening within these vegetated fields. Why is this happening? Well, I've got some data to explain what's going on. So this is a study that we have done again in emergent vegetation. Here we're looking at black mangrove specifically, so flow fields full of mangrove nematophores, which are kind of the aerial roots of the mangrove tree that they send up for aeration purposes. So we're looking at two different densities of vegetation of nematophores, dense and a sparse site, and then we've got a bare sediment control as well. And so we're taking velocity and sediment transport rates through these three different sites simultaneously over a couple of flood tides. What we see is that the velocity decreases predictably from the channel, where we're measuring 5 to 10 centimeters per second, into that bare sediment control area, where flow drops to about 1 to 2 centimeters per second, and then it becomes very, very low within those mangrove nematophores. So less than 1 centimeter per second, especially at that dense site, right? So we've got like 1/10 of a centimeter per second velocity in that dense mangrove nematophore site. And if we look at the difference in turbulent characteristics between the sparse nematophores and the dense, whether we look at the turbulent kinetic energy, the turbulence intensity, or the dissipation rate, all of our data are indicating that the sparse vegetation has a much larger amount of turbulence being created than the dense. And this isn't actually that surprising. So we have to think about the dynamic feedbacks that are happening among three different variables of the canopy's density, the mean flow speed, and the turbulence. So as the stem density or solid volume fraction increases, the turbulence is also going to increase because there's increased element-generated interaction. But usually we're going to find that this reaches a maximum before decreasing with any further density. And that's because of the conversion of kinetic energy due to drag against those same elements is simultaneously leading to a decrease in the overall mean flow speed, which then in turn is suppressing turbulence. So these data are really perfectly illustrating the dueling turbulence controls of the biological canopy. The greater density of the canopy in the dense site suppressed the mean flows up to a point that that excess stem-generated flow interaction still was not able to produce overall greater turbulence. So now we've got the $10,000 question, which is, how is this going to play out in terms of sediment transport? And here we're looking at the suspended sediment concentration that is being measured within the same control volume where we've taken the hydrodynamic measurements. And what we see is, despite that lower shear stress and turbulence, the suspended sediment concentration that is observed in the dense vegetation is exceeding that in the sparse vegetation. You gotta love the nonlinearity of sediment transport. It's kind of difficult for us to compare these apples to oranges because, like I've already said, the flow speeds were different. So we are working on collecting some flume data in a more controlled setting right now that will kind of parse out what is happening, how the physics of this is working. But needless to say, this is a complex problem, trying to be able to predict sediment transport in the complex flow fields. And as it is, sediment transport predictions are exactly what we need for natural infrastructure design for coastal protection. All right, so I'm going to quickly move on to research question number 2, which is, how do the hydrodynamics and sediment transport regimes shape the living environment? So here is an example where we've combined a very high resolution but yet extensive survey of shoreline organisms, vegetation, oyster, with hydrodynamic simulations. So these are numerical results generated by the simulating waves nearshore model. And so by integrating probabilistic hydrodynamic modeling with what we were finding in the shoreline surveying, we're able to find a prediction about where specific organisms are able to live and where they are kind of their habitat requirements are exceeded by the hydrodynamics of the site. What we find with respect to mangrove shown here, so the pink distribution are the sites that have no mangrove vegetation. Green are the sites with mangrove vegetation. What we find when we fit this best fit logistic function between the two distributions is that any site that has an 80th percentile wave height of about 8 centimeters, there's kind of an equal chance that we might find vegetation, mangrove vegetation at that site. Anywhere where the wave height over 20% of the time is over 8 centimeters, it becomes less and less likely that mangrove vegetation will persist. So doing this over multiple percentiles, we can actually come up with a prediction on mangrove site suitability based on wave climate. And so this is something that's really valuable to people who are planning shoreline stabilization. So for instance, if they take a look at their overall portfolio of shorelines that need to be stabilized, we can allow them to pinpoint, this little area right here is our red, our urgent priority for stabilization. And then you can look at, well, how likely is it that mangrove forest is going to persist in this location by itself? So in that study, we were looking particularly at kind of the long-term mature mangrove forest sustainability. But in order to achieve that, we really need to be looking at early life history recruitment. So the establishment of mangrove seedlings and how they're able to interact with the hydrodynamic and sediment transport environment to avoid being dislodged before they can grow into adults. And so here we're looking at a couple of different ways that mangrove seedlings can be dislodged at a young age when the drag force exceeds their anchoring force due to roots, or when the sediment around the roots is eroded, reducing that anchoring force. Right, so this is, I've got a video here of the research in action. Basically, we took a bunch of mangrove propagules, which are the germinated seeds of mangrove trees. When they're released from the tree, they kind of float around in a dispersal phase like this, and eventually establish roots that are able to anchor them into the sediment. So the first phase of our testing was to replicate kind of the tidal pulse, the water level going up and down over time, and see how long and what kind of configuration they were able to anchor in under this hydrodynamic changes of tidal fluctuation. So eventually, after they were able to anchor into the sediments, we started a clock. And when that clock had gotten to 7 days, 14 days, and 30 days, we took the seedling and we tested them in the flume. So we planted them into estuarine sediments in the flume, started adding water to the flume slowly until the seedlings were submerged to their full height, and then subjected them to a scouring flow that was sufficient to erode the bed around their roots. And since we're a little bit short on time, I'm going to just kind of skip ahead in the video so you can... Oh, maybe I'm not able to skip the video, sorry. Eventually, they were removed either through just the hydrodynamic drag force acting on the seedling itself, maybe a little bit of local scouring around the roots that was enough to dislodge them. But what we found is after they had been established for more than 2 weeks of root anchoring, it really took a full-scale bed degradation before the seedling would fail. Okay, so I'm getting to the conclusions, and instead of leaving you with a bunch of bullet points of text, I've made a little just diagram of everything that we've been able to talk about today, relating to the way that canopy properties, including whether or not the canopy is submerged or emergent, how flexible it is, how dense it is, and how it's configured horizontally, how those are going to influence the mean flow, and then turbulence, both directly and through influence to the mean flow, but then bringing in the fact that our organism's life history and some of those hydromorphidynamic thresholds are going to be influencing the canopy properties. So all of that coming from some of the external environmental conditions. So I'm going to end here. I want to acknowledge all of the students and postdocs and my colleagues who have contributed to the science I was able to show you today, and also the agencies that funded the research. If you are interested in the research that you've heard today, feel free to reach out to me. If you're interested in joining research like this, reach out to me. I am recruiting both PhD students and postdocs to start in 2025. And just thanks again for inviting me to come and speak with you today. It's been a real pleasure. And if we have any time, I'm happy to take some questions.
Thanks, Kelly. Let's go around and applause. That was awesome. It's just such a compendium of work on this topic. So it's and really excellent presentation. So we'll go to questions in the room first, and I'll check to see if we have any from Zoom or YouTube. So I know Dr. Altieri on my left here is itching with a couple of questions. So I might break my rule and let you go first.
Oh, thanks.
Yeah.
Thanks. Kelly, it was really nice to see your work and having talked to you casually about what you're up to. It was really nice to sort of see it all come together, and appreciate like the general background on the topic material, people like me. I guess I was just really surprised by some of the, well, what you indicated as being sort of surprised is kind of counterintuitive or maybe contrary to prediction kind of findings that you found in the oysters. Or sorry, it was the seagrass for sure, and even some of the others where you had like talk about lateral flow being, you know, overriding, I guess, like sort of like the kind of within canopy or over canopy movement. So that was, I guess this is more of a comment than a question on that aspect of the work. I guess, yeah, I guess I have, I guess my question would be related to like kind of other habitats and whether like sea level rise, I guess, like that kind of incremental increase in sea level rise. Like I know that some work that's been done in North Carolina shows that oyster reefs can kind of keep up, but perhaps, and this is all very much kind of like rate dependent, but I guess the question I have is based on your knowledge of how these systems are kind of adjusting themselves, I guess, to sea level rise, like the measurements that you make in a bed for like one of these like potential restoration sites, that match between a change in like the morphology of these living structures and, you know, predicted sea level rise. How do you anticipate that's going to affect kind of the flow fields around those structures? Like, does it require, because, you know, kind of active management and kind of remeasurement, or at least over time to kind of get at that?
Yeah, I'm really glad that you asked that question because that's something that I'm really interested in myself. And so one of the reasons that we might choose living infrastructure instead of concrete is so that it can adapt, right? It can change as the sea levels rise around it. And that sounds great in theory, but in practice, how does it actually play out? Because that adaptation, it doesn't necessarily just happen in the same place and they grow vertically, right? So in order to attain like a greater vertical position within the water column, usually what that is going to require is an expansion laterally into a higher elevation area. And so that's where you get into the concept of coastal squeeze, right? So all of a sudden now you're bumping up against the the seawall or retaining wall that is separating the aquatic ecosystem from streets and railroads and utilities and things like that. And so there just isn't any space then for the organism to do what it is meant to do and grow upward by growing laterally upward. So management certainly is going to be one of the most important things that we can do to allow the best chance for that infrastructure to grow vertically upward by growing landward. But from an engineering standpoint, we can also just understand like your question about, well, what if, you know, that oyster reef, let's say, is staying at the same elevation and the water rises around it. That's one of the most important parameters that's going to dictate the flow biology interaction is how deep that water is above it, especially if we're interested in kind of the hydrodynamic attenuation. So as it becomes more deeply submerged, it's going to be less effective at attenuating hydrodynamic energy. The other problem is that oysters actually do mind where they live, right? Sometimes because of ecological pressures, they prefer to live intertidally, and sometimes they prefer to live subtidally. And you can't really force an oyster to live in a place that is not going to be its, ecological maximum. And so an intertidal oyster that is wanting to spend some portion of its day not under the water so that it can escape predation from, underwater predators isn't going to be able to thrive in a subtidal environment. It needs that space to move laterally into its preferred vertical zone. Does that answer your question?
Yeah, that's certainly like, it's kind of what I was afraid of, is that it sounds like you're gonna have some long-term employment prospects, because it sounds like we're gonna need you as these systems continue to respond, and there's some site-specific challenges that need to be dealt with, so thank you.
That probably applies to everyone sitting in your class. So I'm glad you guys have chosen this field. There's unfortunately plenty of work for all of us.
We have a couple questions from YouTube. So Matt Cohen says, excellent presentation. Wondering if there are regulations about boat wake periods during propagule establishment that might follow from the last result. And I'm going to give you that one and another one, and you can try to answer both as we get close to the end. So boat wakes about propagule establishment. And the other question from Alexandra Bijak about dense seagrass beds, how dense seagrass beds might affect the recruitment and establishment of seagrasses. See if you can answer those two at the same time. No,
Yeah, sure.
Or just one. Yeah.
Okay, so wake management is a tricky question. So I can understand there would be a great interest in trying to decrease some of the really high magnitude hydrodynamic forces that are coming from boat wakes during a time when you've got like a sensitive organism that's trying to establish. I think it would be a great kind of environmental management thing to pursue. And we do have wake restrictions, like no wake zones. If you've ever been boating in like a recreational boating area, you may see signs that say, oh, this is a no wake zone. But if you actually dig into what that means, it means that you have to maneuver your boat at the slowest speed that you possibly can safely. And if you're driving a pretty big boat, that can still create a really big wake. So it's more kind of just asking boaters to be a little bit sensitive about the wake that they are creating. We do have shallow water, no wake zones. These are usually, I think, done by county ordinances, so rather than a state of Florida ordinance. But I know Brevard County, for instance, will have no wake zones that are close to the shoreline. And this is usually known as a manatee zone. The reason that they're in place is to avoid boaters hitting manatees. And so I think something like establishing times of year that people could pay special attention to the wakes that they're creating with their boats is a great idea. I'm not certain that it would fly politically. And even if we more environmentally minded kind of folks would really want that. So, recreational boating gets people who are not environmental scientists out on the water interacting with their ecology and, concerned about things like shoreline protection and biodiversity. So I think any type of restriction that might cause people to not interact with their environment, you have to be a little bit careful about unintended consequences of a policy like that. So I don't know if that really answers your question, Matt, in a satisfying way. Then the second question was about seagrasses and if dense seagrass beds create the environment that is right for expansion of the seagrass bed, if I understand correctly.
Like the very dense, the turbulence and shear stress you found in these very dense environments, like how that relates to the flexible vegetation of a submerged aquatic.
Yeah, so I don't know the answer to that in particular, but I can speculate a little bit, right? So as the density increases, you would expect to find really, really slow kind of velocities within that dense seagrass canopy, which could have the effect of maybe not allowing in, kind of enough exchange of gases or something like that. So something that we found, we're studying hydrodynamic thresholds related to seagrass right now. One of the most important parameters, of course, is depth, right? Like the light limitation. But if we look at our data within different depth bands, so in shallow water, kind of moderately shallow, and then in deeper water, what we're finding is that seagrasses that live in deeper water actually, in moderately depth water, let's say, actually prefer a more hydrodynamically energetic environment than those that are living in shallow water. And then the restriction kind of, it almost reaches a peak and then goes back down again. So what that's telling me is that there is some benefit to having, more hydrodynamic movements within the seagrass canopy. I can't tell you what that benefit is at this moment, but I think you might be onto something that, as seagrass increases in density, there may be kind of like a negative feedback towards the success of the seagrass bed.
All right, thank you. Let's give another round of applause to Dr. Kibler. Thank you so much for zooming in with us. I know that Dr. Altieri was hoping to chat with you more in person, so maybe he'll follow up, and I'd like to as well. I've got a student looking at some submerged aquatic veg in springs that I think we're finding some similarly confusing issues about density and the vertical velocity profile. So we'll be reaching out. Everyone, next week we have Dr. Elliott White Jr. from Stanford. He's going to be zooming in, unfortunately, but he's going to be talking about leveraging machine learning for coastal freshwater floodplain ID and habitat suitability. Until then, everyone take care of yourselves and see you later. Thank you, Kelly. Appreciate it.
Thanks, everyone.
Stop the recording and the Zoom here.